Hello, this is Ian Vogelesang, and this is the Introduction to IV presentation. IV is a new block storage synthetic workload generator with real-time dynamic feedback control and a workflow engine. Why did I build IV? My long-term goal is to automate performance testing, so we want to be able to have a workflow engine to automate a test suite workflow. And we want to use the dynamic feedback control feature to perform tests in the theoretically minimum time possible. And through a combination of these two, we can substantially reduce test time and test cost. We can improve time to market. We can significantly improve the quality of the measurements that we make, and we can automatically calibrate sales sizing tools. And then the more short-term goal for manual testing is to significantly simplify setting up manual tests. Just say, for example, that you want to test selecting HTTP pool ID equals 0 and 2, and let IV figure out which LUNs on which test hosts you want to use. And then with IV, it's very easy to verify that the test configuration that you're getting is really what you intended to set up. You can find out if your setup worked okay. For example, you just say create rollup port quantity 64 max droop 20%, and then IV will automatically validate that there are 64 ports reporting and that none of them is showing an IOPS that's more than 20% below the IOPS of the fastest port. So like I said, it's very easy to validate that your test setup went okay. And then another objective is to be able to do things like find the IOPS to obtain 1 millisecond service time. And this uses the dynamic feedback control feature, because normally you impose a workload on the subsystem, a given IOPS, and then you measure what service time or response time you're getting. But with IV, you can do it the other way around. You can specify a service time target, and you can dynamically find the IOPS to hit that target, and I'll show you an example of that later. And then finally, when we're making all of these measurements and we're publishing them to customers, by making IV open source, then customers can audit the source code, and they can be confident that the measurement results really are what they appear to be. Then in terms of the IV architecture, the entire key comes down to what it means to make a valid measurement. Valid measurements are repeatable, meaning that if you run the test again, within the specified plus minus experimental error, you will get the same result again. And then we'll observe that in order for a test to be repeatable, you have to be measuring a steady state condition, because otherwise it won't be repeatable. So the two things to keep in mind as we look at the IV architecture and how IV works is that after imposing a workload on the subsystem, number one, we need to wait for the behavior to settle down into a steady state, waiting for initial transient conditions to settle down. And then number two, depending on how much noise there is in what's being measured, measure for long enough to be confident you've obtained a valid measurement to the specified plus minus accuracy. Keeping that in mind, we can look at the IV architecture. There's a main thread which fires up on the central control host, and then you specify the name of an IV script program. At the beginning of the IV script program, there's a host statement that specifies a range of test hosts. And then for each test host, it fires up a controlling subthread on the master host and a corresponding instance of the IV slave executable on each one of the test hosts. And from there, you're ready to create workloads. Workloads are attached to LUNs on each test host. You can create a workload with the same name on different LUNs on different hosts. Each workload thread uses an IO sequencer plugin to generate IOs in scheduled start time sequence. And we try to keep a few IOs pre-computed and ready to go at all times. And the the generalized interface allows the use of any I/O pattern generator. The current ones we use are synthetic workload generators, but in future we could also use a playback mechanism. And then what's very key is that we're using C++ with the Linux kernel asynchronous I/O interface, which means that a single workload process thread can drive any queue depth up to the limits of the OS HBA with state-of-the-art minimal CPU overhead. So Ivy features very low CPU overhead, which means that it's very responsive to timestamp I/O completion events accurately, and it can very accurately issue I/O operations at the appointed starting time, because most of the time the CPU is idle. And that gives us lots of CPU left over, so that in the future we can compute synthetic workload patterns of a high degree of complexity. An IV test is a sequence of subintervals, typically 5 seconds long. And then there's a cycle that we go through at the end of every subinterval. First, near the end of the subinterval, very near to the end. If we do have a command device connector, and more on that later on, subsystem data are gathered and rolled up centrally to the master host. Then at the end of every subinterval, as soon as the subinterval ends, we roll up the statistics of what happened during that subinterval on that workload thread up centrally to the master host. And at this point, at the master host, we've got both the subsystem data and the host data, and it's all rolled up into the different roll-up instances, and we'll talk about roll-ups in a minute. And then optionally at that point, if you're using dynamic feedback control, we can send out I/O generator parameter updates to all the leaves on the tree. So that's how we accomplish dynamic feedback control. So it's once every 5 seconds, we update it. And after a short delay within the next subinterval, it's actually fairly short. The effects of the previous subinterval immediately have an impact on for example, the IOPS that are being used in the next subinterval. And then finally, once the optional dynamic feedback control updates have been sent out, the master host tells each leaf on the tree to either continue or to stop. And at the end of the test, it'll say stop. So that's how we do dynamic feedback control. Then the next thing to show is that a successful test step, and a test step is a subinterval sequence, has 3 phases. There's a warm-up phase, there's a measurement phase, and there's a cool-down phase, and each of these is comprised of subintervals. During the warm-up phase, we're either allowing time for or expressly waiting for initial transient conditions to settle down. And there's a warm-up seconds parameter which specifies a minimum warm-up period, which, if we use the measure feature, may be extended to wait for initial transients to die down. When the test step is declared a success, the results of the test step are defined as the averages or totals over the measurement phase, and the measurement seconds parameter specifies the minimum measurement period, which the measure feature may further extend. And then a test step may be declared a failure in the event that you're using the measure feature and it reached the timeout seconds parameter value without observing a valid measurement. In this case, all the subintervals are posted as warm-up subintervals, and you don't get a measurement for that step. And then finally, during the cooldown phase, we're running at least one extra subinterval, continuing to drive the workload, so that even with some time jitter across test hosts, the full workload will have been running throughout the measurement. Then, if you do have a command device connector and you're using the default cooldown by right pending equals on feature, then Ivy will subsequently keep running more subintervals during the cooldown phase as necessary with IOPS equals 0 until we see that right pending has emptied. There are 2 parameters that control the measure feature. The first one is called accuracy plus minus, and what this means is extend the warm-up as necessary until initial transients die down, and extend the measurement period as necessary until we've seen enough to be sufficiently confident that we've made a measurement to the specified accuracy. That's the main one. The confidence, I usually let it default, but confidence equals 95%. The confidence parameter expresses how confident you need to be that your measurement falls within the specified plus or minus range around the long-term average that you would get measuring forever. The default of 95% means that 19 times out of 20, the measurement that you make over the measurement period falls within the accuracy plus minus range of what you would get measuring forever. Okay, so these are part of the standard statistical formulas that all scientists use when they're making observations. And it's both convenient and effective to use these standard statistical formulas. You can click on this link here to get a complete description of it. It's for the math literate. And I would say that the one thing where the scenario using IV doesn't fit the assumptions made in the formulas are that the formulas are for samples drawn at random from a large population. Whereas with IV, the behavior or the measurement for one subinterval is related to those for preceding and succeeding subintervals, thus gaming the system to a certain extent. And playing around with IV, my rule of thumb to correct for this is specify an accuracy plus minus parameter value with a 2 times safety factor, and you'll be okay. In other words, say accuracy plus minus equals 5%, and you'll be safe that you'll get repeatability within plus or minus 10%. So these formulas are both convenient and effective, and you use the rule of thumb to specify an accuracy twice as tight as what you're looking for, and it works great. In this introductory presentation, we're showing some measure parameter options. You can measure IOPS, you can measure megabytes per second, service time, and response time. These are shorthand for a particular combination of more detailed parameter settings, and see the IV Programmer's Reference Part 2 for a description of the full set of parameter values. To illustrate the concept of the measure feature, I've made a chart here that has 2 sequences. I made these with Excel just to illustrate the concept. In both the blue line and the red line, the long-term average of the line is 1,000 IOPS. The idea here is that if you'd specified measure equals IOPS, accuracy plus minus equals 5%, and then the measure feature had observed as a series of measurements from subinterval to subinterval. Perhaps at this point, if we'd received the series of blue observations, maybe by that point we would have seen enough to be confident 19 times out of 20 that we had made a measurement within plus or minus 5% of the long-term average. We could have stopped the test there right away. Whereas if we had received the series of measurements represented by the red line, by this point we wouldn't have seen enough yet to know what the long-term average was, and the test would continue out long enough until it became apparent. The IV measure feature extends the test until enough measurements have been made to be statistically confident that the average of the bi-subinterval values is within a specified plus or minus accuracy variation from what the long-term average would have been if you continue the test indefinitely. You can be sure that when IV says it has made a measurement, that it's a valid measurement. And then this is an actual illustration of operating on an older Hitachi array, and we can see the measure feature in action at the moment when it had detected and made a valid measurement. And here you can see a red line, which is on the IOPS scale on the left, and a green line, which is on the IOPS scale on the left. And these are the IOPS from subinterval to subinterval. And then in addition, in this case, we had a command device connector. So the blue line is showing on the right-hand scale what the percentage write pending, or the percentage of cache that had dirty data waiting to destage to disk, is shown just for your information. That's shown on the right-hand curve. But what we can see here is that at this point at subinterval number, 78 or 79 or something, when we look back from the current subinterval and we look back at the measurements over the preceding subintervals, we look further and further back until we have seen enough, bing, in this case, to have made a measurement. But if we tried to do that from this point in time, we would have gone back into where the red line is here, which means that the variation would have been too much and it wouldn't have matched. So this is the moment in time when, looking back from the current subinterval that just ended to the preceding series of subintervals, that the measurements were accurate to plus or minus, within plus or minus the specified accuracy. So what I'm saying is that Ivy is effective. This feature is effective to reject initial transient conditions and wait for it to settle, and then measure once it is settled. So it's effective to do that. In an initial test where we replicated what we call a scalability test suite, we go through several hundred combinations of input parameters using a standard scalability test tool. And for each combination of, for example, reads and writes and block size, for each combination we run for a fixed 6 minutes. That's how we normally do the testing. So I just created an Ivy test suite replicating the series of tests with all the different combinations of input parameters that we normally do to characterize the performance of an array or a drive type or something like that. And what we saw was that the overall test runtime decreased by 60%. And this is because the vast majority of the time the workloads settled down quickly and were then stable, so we didn't need to test for very long. But it turned out that there were a few cases where it took a long time for initial transient conditions to settle down, or that where on an ongoing basis there was an instability in the workload on the subsystem, and because of the variation from subinterval to subinterval, we needed to sometimes run for as much as 20 minutes to get an accurate measurement. So the interesting thing here is that the use of the measure feature substantially reduces test time, while at the same time improving the quality of the measurement data. Ivy is open source, and it's designed to be multi-vendor or vendor independent, and the way that it does that is that it uses an external tool to define the attributes of the LUNs that you can select on. The Hitachi LUN Discovery tool is open source. Here's the link where you can click on to get it, and it produces a CSV file that looks like this, with a header line with column titles, and then a detail line for each LUN that shows the attribute values according to the column titles. And then in order to provide support for another vendor's architecture or terminology in Ivy, in order to be able to use Ivy on another vendor, all you have to do is produce a CSV file that's got a header with attribute names and a body with lines for each LUN, showing what the values are for each of the attributes for that LUN. And then in Ivy, these column header titles become selectable. And you can say, for example, select port is 1A, 3A, 5A, and 7A. And port, the string was taken out of the header column here. And then the 1A, 2A were taken out of this column here. So automatically in Ivy, you can select port is one of these, and it will pick the right ones on the right hosts. Then there's a command device connector, which is a proprietary extension to Ivy. It's not part of the Ivy open source project. It's available only for authorized use in Hitachi Labs with a license key mechanism. And as long as the license key and the software are installed on the test host that sees the command device, when you start the test, Ivy will automatically notice, will discover that there is a command device and will exploit it. It will retrieve the subsystem configuration data, and then the attributes defined by the original CSV file from the SCSI inquiry tool are augmented by the corresponding additional attributes of those LUNs that were obtained by correlating the subsystem configuration data with the original SCSI inquiry data in the CSV file. And that also enables it to build a filter for each rollup instance, which we'll talk about in a minute, to show which hardware components are behind or associated with each one of the test LUNs. That allows you to filter the real-time subsystem performance data. Then, as the subintervals are running with the Hitachi command device connector, it retrieves real-time subsystem performance data aligned with the test subintervals, and therefore it records automatically in CSV files for each subinterval the subsystem data, and that's all correlated exactly with what's going on the hosts at the same time. So that enables you to do real-time dynamic feedback control of the host workload based on real-time subsystem performance data. And in this presentation, we're going to show you two examples. One of which was operating on MP core %busy within the array, within the subsystem, and the other one was done at a percentage of parity group %busy on the subsystem. And then finally, the command device connector checks that the subsystem doesn't have any failed components. And we encourage other vendors to make your own proprietary connector extension for Ivy. Collect the subsystem configuration data, collect real-time performance data, have Ivy record that performance data correlated and aligned with the host measurement data to facilitate development of modeling tools, including sizing tools. And then that will also enable you to use dynamic feedback control to find the IOPS associated with a particular target value for some metric in the array, like microprocessor busy or drive %busy or cache write dirty, %full, etc. And then what I will say here at the same time is that the output from the demo runs uses examples of output collected when using a Hitachi command device connector, and that's there to show you that it's easy and straightforward to do with Ivy. You can write your own connector and you can do dynamic feedback control on your own stuff. Okay, the core of how everything in Ivy works is the rollup. And every workload thread on every test host is represented in exactly one instance of each rollup. There is, by default, always a role called all, which has one rollup instance, all equals all, which consists of all workloads on all LUNs on all test hosts. Then from there, you can define further rollups. Each user-defined rollup name must be a combination of one or more LUN attribute names. And the example at the top here, create rollup port, is the statement that you'd use to get a rollup for each port name, all the workload threads that correspond to that port, like 1A. And is an example of a combined rollup name of more than one attribute to get data. If you're testing multiple different subsystems and port 1A, there's a port 1A on this subsystem and a port 1A on the other subsystem as well, then you could define a rollup called serial number plus port. And then you would get instances of that rollup, such as serial number plus port equals, and then here's a serial number of an array and a particular port name. Okay, so that's how you create a rollup. Everything in Ivy works using rollups. First of all,
you create a roll-up in order to get CSV files sliced and diced by that thing. If you want a CSV file by parity group, you want a CSV file by port or by LDEV or by whatever, you create a roll-up on that attribute, and then you'll get CSV files broken down that way. And then the next thing is that both the measure functionality, the seen enough and stop functionality, and the dynamic feedback control functionality, both of those operate at the granularity of the roll-up instance. They're fine-grained. So in other words, if you say measure to plus or minus 5% accuracy on, and then you say do that by port, then the measure function will select a measurement period where for each individual port the measurement was accurate to plus or minus 5% over that measurement period. And then for the dynamic feedback controller, it would control each one of the sets of workloads independently based on what the measurement data was for that particular port. Okay. When you set a configuration up in a lab, say you're cabling up 64 paths, it's really common to have one cable that's broken or isn't working properly. And for that reason, in Ivy, in order to improve ease of test setup and improve the quality of the measurement data that we produce, you can also create a roll-up to validate the quantity of a certain instance of a thing. For example, if you say create port quantity 64, then Ivy will invalidate the result if we don't get data for exactly 64 ports. And if you also say max droop equals 20%, then it will invalidate the data if there's any one port whose IOPS is more than 20% slower than the fastest port. So even if they're all there and reporting if one of them's limping along instead of running, then you can automatically invalidate the data. And then on this chart, we're showing two different things, one of which is the idea of an automated workflow. Because IvyScript is a programming language a bit like C, you can run tests and then based on what you observe, decide what to do next and build this all up into an entire test workflow. And this is an example of a 3-step workflow. And then the second thing that we're showing on this chart is the concept of dynamic feedback control. Each one of these lines represents a subinterval sequence where we were shooting for, we were doing dynamic feedback control on the service time that we were measuring, and then at certain, we did one run for 12.5% higher than the baseline, 25% higher, 50, 75, 2 times the baseline service time, and all the way up to 5 times the baseline service time. So we did a series of runs. On each run, we set the target service time. And here you can see subinterval by subinterval what the IOPS were, and you can see it how long it takes to reach a stable thing, and then it's measuring after that. So in the first step, what we do, not shown, is we measure with IOPS equals max. That's the maximum number of IOPS we can do. And then in the second step, also not shown, we run at exactly 1% of the maximum observed IOPS in step 1, and we measure the service time. And we call that the baseline service time. So those two things aren't shown. And then for each of the colored lines here, it's a third step, which does dynamic feedback control based on a target percentage of the baseline service time. Okay, so that's an automated test workflow. And then this is the actual CSV file output showing what the measurement value was for that series of colored lines. We have here the baseline measurement point, which was the step 2 baseline service time, and it shows IOPS and service time. And then for each of those colored lines, this shows the measurement point at 12.5, 25%, 50%, etc., up times the baseline service time. So what we're saying here is that we've written a program that's auto scaling. It doesn't really matter whether it's a 7200 RPM SATA drive or whether it's an SSD. If you want to know what the IOPS versus service time curve is for this resource, you just point this thing at it and it will automatically do it right. And there again, we're showing that Ivy is designed as a workflow automation tool where we can write an entire script of a series of tests, and based on what happens in a previous step, we can auto scale what we do in the next step, or we can decide what to do next at all. Here, there's two charts that show you doing dynamic feedback control on command device connector data. And in this first example, we're doing dynamic feedback control of the IOPS to hit 10%, 20%, 30%, 40% busy, each of those in a subinterval sequence. And then I'm only showing the second chart where we show the results. And here we can see that when we tried to get 10% busy parity group by varying the IOPS, we were actually able to get 9.95, et cetera. And here we can see that this is highly effective to achieve the target percentage parity group busy in the array, the dynamic feedback control. And this allows you to directly calibrate modeling tools, for example. And the curve, you can see it tilts up at the end here because these are HDDs, and as the drive percent busy goes up, then there's a proportion, as it does, reordering of in-queue IOs according to reduce the mechanical positioning time, to reduce the rotational latency, and the seek time. Then we can fit more IOs in the same amount of time, and therefore the curve tilts up at the end. Okay. And then in this case, we're showing the concept of fine-grained dynamic feedback control. For each of these set of columns, this was a single run of Ivy, and we specified that the dynamic feedback control was supposed to be pointed at the MPU rollup. So dynamic control of the IOPS at the same time for all of the MPUs. Each of the MPUs had its own dialed-in IOPS going up and down to make that MPU hit 10% busy. So each of these column groups represents a single test run, and we ran at 10%, 20%, 30%, and 40% busy. And then we can show you here that the ratio, the average amount of processor busy time per I/O was different on the 4 MPUs. And then I wanted to also show you that Ivy doesn't only record average service times, but it records distributions of service times. Here we can see a scale at the bottom from 0.1 to 1 millisecond in 0.1 milliseconds, and then in steps of 1 millisecond up to 20 milliseconds, and then in steps of 10 up to 100 milliseconds, and then in steps of 100 up to 1 second, and then up to 10 seconds here. And so this is what all of the data, all of the time, and all of the flavors is recorded in with a histogram like this. And then it's very useful. And the reason you get this, there's a change of scale at a breakpoint at this point, and that the curve is actually smooth, but that's just an abrupt change of scale on the thing. But this lets you see if there's any stragglers or if there's anything funny looking in the distribution of the IOs. And then what I would say here is when we're quoting write service times, it's meaningless talking about what the write service time is at IOPS equals max, because at that point the array these stages can't keep up with you and it's holding you back. So here I'm showing what the write service time is at 90% of the max IOPS. We measure once what the max IOPS is, and then we run at 90% of that, and then we show you here what the resulting service time distribution was. And even at 90% of the max IOPS, you can see that pretty much all of the IOs finish in a small fraction of a millisecond. The one final thing was to talk about the concept of layering workloads at different locations within the LUN. For example, you might want to put a random workload in one area of the LUN, and then several other sequential workloads, each in their own area within the LUN doing I/O sequentially within that zone. And just to show you the concept of that layering of workloads at the same time, this graph only ran one of them at a time, but it created 200 zones from the beginning to the end of the run. And then we did one subinterval sequence for each of those 200 zones, and we measured what the read throughput was, and we did another run where we measured what the write throughput was. And we can see here that for the reads, we can see a staircase pattern which corresponds to the zones in the disk drive. The outer zones have more sectors in them, and therefore the data transfer rate's higher. So we can see for the reads, we're actually gated by the performance of the disk drives all the way through. Whereas for the writes, we can see that there was another factor which was limiting throughput all the way up to where we were getting so close to the inside of the disk that the data transfer rate of the average sustained data rate went so low that the drive became the bottleneck factor at only right near the end. So to summarize about Ivy, it's first of all, it's written in C++ and it uses the asynchronous I/O interface. This means you get the lowest CPU overhead, minimizing the cost of test host hardware and maximizing the measurement accuracy that we're going to get, because most of the time the CPU is idle. And it's designed for open source and vendor independence. We made it super easy to add support for another vendor, and being open source, you can look at the source code and you can contribute if you want to test something different. And for manual test runs, it's super easy to set up because you can directly select by whatever attribute that the LUN has. You can select by any one of those attributes, and Ivy automatically figures out which LUNs and which hosts those are. Then with the measure feature, we can measure for the minimum theoretically possible time to make a valid measurement to the specified plus or minus accuracy. And then because we have real-time dynamic feedback control of the workload, we can find what IOPS is needed to obtain 1 millisecond service time. And then in terms of producing the quality of the output, we record only valid measurement data. Not only do we measure for long enough to obtain a statistically valid measurement, but we can invalidate that measurement if the test setup didn't have the right number of ports reporting, let's say, and that none of those ports was running significantly slower than all the others. And of course, we've demonstrated automation of a workflow using IvyScript programs to show that we can automate entire test workflows. Right now, August 13th, internal HDS performance team user beta test is in progress, and including testing of dedupe and compression support, which is covered in another presentation. Ivy has been released as open source. It's on GitHub. We've got support for several generations of subsystem. And in terms of looking forward, there's a long list of to-dos, but some of the bigger ones are, one idea is to repackage access to the Ivy engine to offer each Ivy engine control statement as an API call, and then to build a CLI on that RESTful API to enable programming Ivy in the programming language of your choice. That would be a big big deal. Another important one is to develop an automatic gain control feature for the PID loop. The PID loop is very effective. However, you need to use the correct parameters, the volume, the gain on it, and to make this one foolproof and to avoid iterative experimentation by the poor user, we need to develop automatic gain control for this. There's a long list of other things. Okay. Thank you very much.